All right, in this section, we're going to talk about section 4.2, dealing with the addition rule and the multiplication rule. And in this section, we'll develop the ability to calculate the probability that in a single trial, some event A occurs or some event B occurs, or they both occur. That's applying the addition rule by correctly adjusting for events that are not disjoint or overlapping. Also, we'll develop the ability to calculate the probability of event A occurring in the first trial and an event B occurring in the second trial. This is where we apply the multiplication rule by adjusting the events that are not independent. Also, we'll distinguish between independent and dependent events. Okay, so that's what we'll look at in section 4-2. So in this section, we're going to present the addition rule as a tool for finding the probability of A or B. And that's the probability of that either event A occurs or event B occurs, or they both occur as the single outcome of a procedure. And the key word in this section is going to be the word or. Okay, and that means we're going to add the probabilities. And here we're going to use the inclusive or. And that means either one or the other or both. That's the inclusive or. Okay. Also, we'll look at the basic multiplication rule that's used for finding the probability of A and B. And that's the probability that event A occurs and event B occurs. So if the outcome of event A somehow affects the probability of event B, it is important to adjust the probability of event B to reflect the occurrence of event A. Okay, so we'll start this section by giving you some definitions here. A compound event is an event or any event combining two or more simple events. All right, now the first rule we'll talk about is the addition rule. And that's this: the probability of A or B, and this is the notation. That means that probability in a single trial, event A occurs or event B occurs, or they both occur. So here we're using that inclusive or in this section. So when finding the probability that event A or event B occurs, find the total number of ways A can occur and the number of ways B can occur. But you have to find that total in such a way that no outcome is counted more than once. Okay, you want to exclude the overlap in events A and B. So here's the formal addition rule that we'll deal with here. The probability of A or B is going to be equal to the probability of event A plus the probability of event B minus the probability of A and B occurring. Okay, so here the probability of A and B denotes the probability that A and B occur at the same time as an outcome in a trial or procedure. Okay. Now, on the next page is the intuitive addition rule. And that's just to find the probability of A or B, you're going to find the sum of the number of ways event A can occur and the number of ways event B can occur, adding in such a way that every outcome is counted only once. And the probability of A or B is equal to the sum divided by the total number of outcomes in the sample size. Okay. Now the addition rule is simplified when the events are disjoint. So here is a illustration of just that. Okay. So here's another definition of what we mean by disjoint. Events A and B are disjoint or what they call mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. In this case, if you look at the illustration on the left side, you see a Venn diagram for events that are not disjoint. Okay, the red circle is probability of event A. The yellow circle is the probability of event B. If you look at the intersection of the yellow and the red, you'll see the probability of A and B. That is not disjoint because there is an overlap in those two probabilities. Whereas on the right side, you'll see probability of event A in red and the probability of event B in yellow. Those two do not intersect. Those are considered to be disjoint events. Event A and event B have nothing in common. Okay, so whenever A and B are disjoint, then the probability of event A and B becomes 0 in the addition rule. And that means we end up with the following: the probability of A or B equaling to the probability of event A plus the probability of event B. Now, this is only when events A and B are disjoint events. On the other hand, if you have events that are not disjoint, like the one on the left side, then you have to use the formal addition rule. Okay. Now let's look at a few examples of what is considered to be disjoint and what is considered to be not disjoint. Like this one. In this first example, we want to decide whether the following two events are disjoint. Like in number one, electing a president of the United States, and number two, electing a female candidate. Well, let's think about this. It is possible that if we elect a president of the United States, that president could be a female candidate. So those two events are not disjoint, because it is possible for the president of the United States that a person elects can be a female candidate. So this is not disjoint. All right, number two. Randomly selecting a statistics student and getting someone who brings a pen to class. And then the other one is randomly selecting a statistics student and getting someone who brings a textbook to class. In this case, it is possible that a statistics student could bring a pen and a textbook to class. Those two can overlap. It is possible. So that means these two events here are also not disjoint. So these two events are not disjoint. Okay, and I do have another example. Determine whether the two events are disjoint for a single trial. Randomly selecting someone who plays soccer and also randomly selecting someone who takes a history course. Well, it is possible to select someone who plays soccer and takes a history course. That can happen. So these two events, again, are not disjoint. Now, I apologize for just giving you events that are not disjoint. An example of a event that is disjoint would be electing a senator who is Republican, and then the other one is selecting a senator who is a Democrat. It is impossible to elect a senator who is both Democrat and Republican. He's one or the other, or she's one or the other. So electing a Democratic senator and electing a Republican senator, those are considered to be disjoint events. Okay, now here's a summary of the key points in this section. To find the probability of A over B, you want to begin by associating use of the word or with addition. And then number 2, consider whether events A and B are disjoint. That is, can they happen at the same time? If they are not disjoint, that is, they can happen at the same time, you want to be sure to avoid or compensate for any double counting when adding the relevant probabilities. If you understand the importance of not double counting when you find the probability of event A or B, you don't necessarily have to calculate the value of this right here. Probability of A plus the probability of B minus the probability of A and B. But it'd be best to try to use that formula if at all possible, if you can try to see it from a table. All right, next we'll talk about complementary events and the addition rule. If you recall, back in section 4.1, that A with the bar on top is used to indicate that A does not occur. We are certain that either event A occurs or it does not occur. Thus, it follows that the probability of A or A complement is equal to the probability of event A plus the probability of A complement. That's equal to 1. Because events A and A complement must be disjoint. This result of the addition rule leads to the following 3 expressions that are equivalent in the same sense that they are different forms of the same principle. So on the left, you'll see the rule for complementary events. The illustrations in this Venn diagram here. In the yellow circle, that's the probability of event A. The shaded area in red, that represents the probability of A complement, which is actually 1 minus the probability of event A. Okay, and that the rule for complementary events states here, the probability of A plus the probability of A complement is going to be equal to 1. Those sums will be equal to 1. The probability of A complement will always be 1 minus the probability of event A, and the probability of event A would be equal to 1 minus the probability of A complement. All right, let's use this in example 4. And it states here, a research center poll showed that 83% of people believe that it is morally wrong to not report all income on tax returns. What is the probability that someone does not have this belief? Okay, so let's look at what's given to us. The probability that someone has the belief that it is morally wrong to not report all income on tax returns is 83%. So 83% as a decimal, if you recall. Drop the percent sign, move the decimal point 2 places to the left. It will be 0.83. Now, what is the probability that someone does not have this belief? So the probability of no belief is here. This is just a complement. So we got to do 1 minus the probability of someone that does have the belief. So we got 1 minus the probability of someone having the belief will be 0.83. So 1 minus 0.83 would end up being 0.17. So the probability that someone does not have the belief that it is morally wrong to not report all income on tax returns will be 0.17. Okay. All right, next we'll look at this example, example 5. It says you use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those indicated in the table. So here's that table where we have 4 different drive-through restaurants, and either the order was accurate or the order was not accurate. If one order is selected, find the probability of getting food that is not from restaurant A. All right, first of all, we need the total of all of these numbers that are in this table. So in this case, if I was to add, and here I'm going to put the calculator in front, figure this out. If I do 325 plus 279 plus 250 plus 146 plus 38 plus 51 plus 40 plus 12. That'd be 1,141 total. And also in this case here, I'm looking at restaurant A in this case, because I want the probability of getting food that is not from restaurant A. Well, let's look at what's from restaurant A, 325 and 38. So let's say restaurant A, this would be 325 plus 38. If I add those two together, that would be 363. So 363 orders came from restaurant A. So the probability that an order came from restaurant A would be 363 over the total number of orders altogether, 1141. And also, let me do this. I'm sure in the homework they're going to ask for this as a decimal. So if I do 363 divided by 1141, and if I rounded that off to, let's say, 3 decimal places, that would be approximately 0.318. Okay. That's the probability that an order came from restaurant A. But they asked for the probability that getting food that is not from restaurant A. So the probability that an order was not from restaurant A so this is going to be 1 minus the probability of getting an order from restaurant A. So in this case, I'm going to have 1 minus that 0.318. If I subtract 0.318 from 1, I'm going to get 0.682. And this is to 3 decimal places. So the probability of getting food that is not from restaurant A would be 0.682. Okay. That's example 5. All right, now example 6. Here I'm going to use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those included in the table. Okay, there's that table there that you see here. And if one order is selected, find the probability of getting an order that is not accurate or is from restaurant C. Are the events of selecting an order that is not accurate and selecting an order from restaurant C disjoint events? Okay, so we need to find the probability of an order that is not accurate or from restaurant C. Okay. What I'm going to do is highlight the order that's not accurate and the order from restaurant C. So here, order is not accurate is this row, and restaurant C is from this column right here. Notice that there is a overlap in those two events. Because here, not accurate is this row, this column is column C, restaurant C. There's an overlap, and the overlap is right here at this number, 37. Okay, so we're going to have to use the formal addition rule to avoid the overlap. So this is just like saying the probability of A or B, that's equal to the probability of event A plus the probability of event B minus the probability of A and B, because the A and B represents the overlap. So in this case here, the probability of selecting an order that's not accurate or from restaurant C would be this, the probability of the order not being accurate plus the probability of selecting an order from restaurant C okay. And then I have to subtract off the overlap. So this is going to be minus the probability of the order not being accurate and from restaurant C. And that's using this formal addition rule that I've written up here. Okay, now the probability that the order is not accurate. Okay, that's this row right here. And let's find out what the total is altogether here. If you were to add each of these numbers individually, you would get 1,119. That's going to be our denominator because that's the total of the entire data set. So here, order is not accurate. We have to add 39, 58, 37, and 11 together. These four numbers added together will give you 145. And that's divided by the 1119. And then plus the probability of getting an order from restaurant C. That's this column right here. Add 248 and 37 together, you'll get 285. And that's out of 1,119. And then we have to subtract off that overlap that I circled in that table. Okay, order not accurate, and then restaurant C has the overlap of this number, the number 37, divided by 1119. And that's to avoid any overcounting. All right, so now these denominators are the same. So all we have to do there is add 145 and 145 and 285, subtract 37 from that, you'll get 393. That's the numerator. This is over 1,119. And they want this as a decimal too. So if I do 393 divided by 1119 to 3 decimal places, this will be approximately 0.351. Okay. Then the other part of the question is, are the events of selecting an order that is not accurate and selecting an order from restaurant C disjoint events? And the answer there is the events are not disjoint, as I illustrated here, because there is an overlap. It is possible to receive an inaccurate order from restaurant C. Okay, so that deals with the addition rule. Now we'll move on to the multiplication rule. And the notation for that would be that's the probability of event A and B. That means the probability event A occurs in the first trial and event B occurs in the second trial. So here, this notation, the probability would be, and then a vertical bar, and then A, that actually represents the probability of event B occurring after it is assumed that event A has already occurred. So we interpret that as event B occurring after event A has already occurred. Some people like to say the probability of event B given A. That is the probability of event B occurring given that A has already occurred. And here's the formal multiplication rule for that. Probability of A and B is equal to the probability of A times the probability of B given that A has already occurred. All right, next page is the intuitive multiplication rule. So here to find the probability that event A occurs in one trial and event B occurs in another trial, multiply the two, you multiply the probability of event A by the probability of event B, but be sure that the probability of event B takes into account the previous occurrence of event A. So when we apply the multiplication rule and considering whether event B must be adjusted to account for the previous occurrence of event A, we are focusing on whether events A and B are independent. That's a B. Events A and B are independent. In general, the probability of any sequence of events, of independent events, is simply the product of their corresponding probabilities. Okay, so now this brings up definitions here of what's independent and what's dependent. Okay, and it's this. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are simply independent of the occurrence of any does not affect the probabilities of the occurrence of the others. But if A and B are not dependent, then they are said to be dependent. Okay. Also, sampling methods are critically important in statistics, and the following relationship holds. Sampling with replacement means that the selections are independent. Now you have to think about this for a moment here. If I have like 8 balls in a bag, and I want the probability of selecting one of the balls, that's of course going to be 1 out of 8. With replacement means I put the ball back in and then I select the second one. The probability of that will be 1 out of 8 still. But sampling without replacement means that the ball will not go back in the bag, for example. And that's going to reduce the probability when I make the second selection. So those selections are going to be what we call dependent events when we sample without replacement. As in example 7. Here we're going to use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those included in the table. Okay, so there's our table here. And this is parts A and B. If 2 orders are selected, find the probability that they are both from restaurant D. And in part A, you're to assume that the selections are made with replacement. Are the events independent? Let's see. So this is with replacement. And we want the probability that both are from restaurant D. Okay, let's look at restaurant D here. In fact, let's look at the total that's in this table. If we were to add each of these numbers up individually in these boxes, that total is 1,104. All right. Now, restaurant D is this column right here. Add 134 and 18 together, you'll get 152. So on the first order, the probability that it came from restaurant D will be 152 out of 1104. Now, with replacement means that selection will be, that first selection will be considered again. So I'm still going to have 134 plus 18, which is still 152 out of 1104 on the second order. Okay. So with replacement, your probabilities are going to remain the same. Now, we need to come up with a decimal value for that. So let me show you how that's going to be done. In this case, that 152 over 1104 is the same. But if you want to do this, we can do left parentheses, 152 divided by 1104, close parentheses, times, and then open parentheses, 152 divided by 1104. Now, if we were to round that off to 4 decimal places, that value will be 0.0190 because the fourth digit here is a 9, to the right of it is a 5. So 89 becomes 90. So I'll have 0.0190. That represents a probability that the selections, that the two orders randomly selected are both from restaurant D, and that is with replacement. And are the events independent? Here, sampling with replacement, it is, the selections are independent. So here we have independent selections or independent events. Okay, so that's part A. Now part B, assume the selections are made this time without replacement. We want to find the probability that they are both from restaurant D. So this is without replacement. We want the probability that they are both from restaurant D. Well, the first order that we select from restaurant D, we're going to be selecting a total of 152 out of 1104. But since we're dealing without replacement, on the second order, that probability is going to be a little bit different because notice the first selection will not be considered. That means the total from restaurant D will decrease by 1. So instead of 152, you're going to have 151 to select. And the total number of orders will drop from 1104 to 1103. So here, the numerator and the denominator will be decreasing by 1 because on the second order is without replacement. That means the first order will not be considered. So here we got 152 divided by 152 over 1104 times 151 over 1103. Now, to 3 decimal places. Here's how we enter this in the calculator. We can do left parentheses 152 divided by 1104, close parentheses, divided by open parentheses, this time 151 divided by 1103, close parentheses. And to 4 decimal places, this would be approximately 0.0188. And then the question is, are the events independent? In this case, without replacement, sampling without replacement, they are dependent events. So here, these are, we can just say that they are not independent events. And if they're not independent events, obviously they have to be dependent events. Okay. And take a look at this example. Here we're going to use the data in the following table, which lists drive-through order accuracies at popular fast food chains. Assume that the orders are randomly selected from those included in the table, as you can see here. If 3 different orders are selected, find the probability that they are all from restaurant B. Okay. Randomly selected. Let's find the total first. Okay, add all these numbers that you see in this table, you'll get a total of 1,097. 3 different orders are randomly selected. Here I'm going to assume that these orders are going to be not independent, dependent. And they're going to be done without replacement. Okay, so we're going to come up with this without replacement. So here, 3 different orders from restaurant B. Well, if there are 3 different orders, then that means they have to be dependent. We're doing this without replacement anyway. Okay, so let's look at restaurant B. That's a 269 and 58. If I add 269 and 58 together, I would get 327. So the first order that I select, that probability would be 327 over 1,097. And then I select a second different order. Well, guess what? I'm doing this without replacement, so that means that the numerator and the denominator would decrease by 1. So I'm going to subtract 1 from 327, that would be 326. 1,097, subtract 1 from that, it will be 1,096. And then the third order is a different order from the first and the second. So again, this is without replacement. So on this fraction, that's going to also decrease by 1. So 1 from 326 will be 325 divided by 1 from 1,096 will be 1,097. Okay. So if you kind of get the hang of this, if you get the first one, the first probability, and then without replacement, the second will be decreased by 1 in the numerator and the denominator. And the third will be decreased by 1 in the numerator and the denominator from the second. Now, let me show you how to enter this in the calculator. All right, I'll do left parentheses 327 divided by 1,097, close parentheses, times, and then left parentheses 326 divided by 1,097. 1,096, close parentheses, and then times left parentheses 325 divided by 1,000. And this should be 1,095. Because that's got decreased by 1. Because if that's 1,097, the next one is 1,096, then 1,095. Then hit enter. Let's see, to 4 decimal places, this will be 0.0263. Okay. So you want to make sure that when you're dealing with without replacement, that your numerator and your denominator decrease about 1 each time for each probability. All right, here's another example. This time we have to create a table. Here we're going to use the following results from a test for marijuana use, which is provided by a certain drug testing company. Among 147 subjects with positive test results, there are 21 false positive results. Among 160 negative results, there are 4 false negative results. Complete parts A through C. And they do give you the hint to construct a table. So in part A, they want how many subjects were included in the study and how many subjects did not use marijuana. And what is the probability that a randomly selected subject did not use marijuana? Okay. So let's create this table. Okay. By row, the first row is a positive test. The second row is negative test. And then I'm going to have the total down here. Now for each column, I'm going to put yes or no for marijuana use. And I'm going to put a total column over here. I'll tell you what, I'll extend it like this. And let's read what we have here and try to fill in from that information. All right, it says here, among 147 subjects with positive test results. So the positive test results, that total is 147. And it says there are 21 false positive results. What that means, false positive means, no, they did not use marijuana, but their test came back positive. So under no and positive test, that number will be 21. And I can subtract 21 from 147 to come up with this number right here, where they used the marijuana and came up with a positive test. That amount is 126. 21 from 147 will give you the 126. And then among 160 negative results, so that 160 goes here. There are 4 false negative results. That means, now let's think about false negative results. They used marijuana, the test came back negative. That would be a false negative. They used marijuana, but the test came back negative. In other words, they beat the test. So that 4 would go here. Now, if I subtract the 4 from 160, that would be 156, which means they did not use marijuana and the test came back negative. All right, let's fill in these total boxes here. For the yes column, 126 plus 4 is 130. For the no column, 21 plus 156 would be 177. And if I add 147 to 160, this will be 307. And if I add 130 and 177 going this way, it's also going to be 307. So my table is complete. So let's answer parts A, B, and C. All right, in part A, it says here, how many subjects were included in the study? Well, guess what? I've already added those numbers. So that's 307 altogether. And even if I didn't have these total rows and columns here, you can add 126, 21, 4, and 156 together to get 307. Part B, how many subjects did not use marijuana? Now I'm going to say not use marijuana. Did not use marijuana. That's this column right here. 21 and 156 together, that would give you that 177. And now part C. What is the probability that a randomly selected subject did not use marijuana? So the probability of not using marijuana well, that's from parts A and B. The number of people did not use marijuana, that was 177, over the total number of subjects that we were dealing with was 307. And if you were to do this in the calculator, 177 divided by 307, let's say the 3 decimal places, this will be approximately 0.577. Because the third number is a 6. This 5 to the right increased the 6 to a 7, so it'll be 0.577. So the probability that a randomly selected subject did not use marijuana would be 0.577. Okay. All right, next we'll talk about treating dependent events as, well, let's start with the exception of treating dependent events as independent. Some cumbersome calculation can be greatly simplified by using common practice of treating events as independent when small samples are drawn from large populations. In such cases, it is rare to select the same item twice. And then treating dependent events as independent, that's a 5% guideline for cumbersome calculations. When calculations with sampling are very cumbersome and the sample size is no more than 5% of the size of the population, treat the selections as being independent. even if they are actually dependent. And here, a tree diagram is a picture of the possible outcomes of a procedure shown in the line segments emanating from one starting point. These diagrams are sometimes helpful in determining the number of possible outcomes in a sample space if the number of possibilities is not too large. In one of the examples that I did in the last video for section 4.1, I had to construct a tree diagram of boys and girls for a family that wanted 4 children. And I had to list all the possible outcomes here. Okay, and this is an example of what that tree diagram looks like. These diagrams are sometimes helpful in determining the number of outcomes in a sample space if the number of possibilities is not too large. Okay, and now we can summarize this that we just got through talking about in section 4.2. The addition rule for probability of event A or B, the word or suggests addition, and when adding the probability of event A and the probability of event B, we must be careful to add in such a way that every outcome is counted only once. And then the multiplication rule, where you have the probability of event A and B, the word and suggests multiplication. And when multiplying probability of A and probability of B, we must be careful to be sure that the probability of event B takes into account the previous occurrence of event A. Okay, and I have a Venn diagram, not a Venn diagram, a flow chart of how to apply the multiplication rule, where in this case here, you have the probability of A and B, that's the multiplication rule. Then you want to ask yourself, are A and B independent? If it is, then just go ahead and multiply the two probabilities together. The probability of A times the probability of B. But if it's not, if A and B are not independent, then you want to take into account that event A has already occurred. So that's where we use probability of event A times the probability of event B given A. And it does say for you to be sure to find the probability of event B by assuming that event A has already occurred. Okay, so that concludes this video of section 4-2 dealing with the addition and the multiplication rules here in this section. So please feel free to email me with any questions if you have difficulty with the homework assignment for this section.